first to the organizers for giving me the opportunity to speak today, but also for the last 4 weeks, because it's been a really wonderful conference. And basically, I want to talk about a paper that I wrote a couple months ago with Dalilio Mesach. And basically, this actually connects to a couple topics that we had in this past workshop in the past 4 weeks, mostly related to 2 papers. For the first one, which most of you hopefully know by this point, is Simon's and Vincent's paper on extremal EFTs, where we'll be sort of using their method as well as basically the uplifting of this paper into AdS2, which was done by Simon, Dalilio, Leonardo, and David. And our paper basically tries to do this uplifting in AdS2 CFT1. So there's a few kinematical differences, obviously, in CFT2, and therefore we'll be using, instead of the functionals that David presented to us in the first week, for those of you who've been here for 4 weeks like me, we'll be using functionals that were actually made by Dalilio and Miguel a bit before the BKB functionals by the 4 people here. So what I want to do, or the aim of this whole program, is that we want to find bounds on IR observables that come from basically requiring UV consistency. So basically bounds on observables of EFTs, and in our case, these observables will be Wilson coefficients in AdS2. And we'll be finding this using functionals on the Bootstrap equation. But before I start with the functionals, I'm actually going to do the very easy version of this first paper and basically sketch the whole story in 2 dimensions, as this will then basically guide us through the story in AdS2, which is just a bit notationally more convoluted, but it's the exact same idea. So let's first start with flat space bounds. So my first point on this is that the bounds that we find here we didn't find these first in any way. There was a paper by Bellazzini and Riva and other people who had already found these exact bounds, which they had actually done by looking at higher dimensions but setting u equals 0. And in 2 dimensions, kinematically, we don't have any spin. And also, from the 3 Mandelstam variables, one of them, u, is always 0. So we only have one free parameter that's related like this, and we'll be looking at 2 diffuse scattering of identical scalars for today that can have some mass. So our paper also looks at fermions for the whole story, but it basically follows the exact way it's been, so I'll be sticking to scalars. So what do we know about the amplitude? This is the usual story. We know that it has to be crossing symmetric. In that case, our amplitude just means that it satisfies this. And we also know that it has some cuts on the real axis, but above and below these cuts and between the cuts maybe, we won't have this amplitude is analytic. And then, of course, the most important part is that in the limit where we take s goes to infinity, we have that that m is basically bounded as long as you take enough subtractions. So the limit as s goes to infinity of the amplitude divided by s squared is 0. So then the usual picture that we can draw on the complex plane, this. And we'll be basically assuming that we'll first work at tree level for now, and that we have some scalar with some mass little m in the IR. And as is some cutoff, which I'll just call big M, we won't assume anything except for these points that I've written down. So as a sum cutoff m, we might have some branch cuts here, and then to make this crossing symmetric, branch cuts here. And then what we want to look at is following contour integral of the amplitude with following subtractions that make it quasi-symmetric. Then this following contour integral, if we take the contour at infinity, is 0. And this is for k larger or equal to 1. So then the usual game is that we can collapse this contour down, and we end up with two parts that wrap as branch cuts, as well as contributions that come from these subtractions, one at 0, one at 4m squared. And we'll end up with 2 residues. Okay. So crucially, and this is the game that we have all the time, we basically have now related something that's in what we call the UV region, where we've just assumed a few things. One of the things I actually forgot is, crucially of course, that the imaginary part of the amplitude is always positive. So that is what we'll be imposing here on these branch cuts. And then we have residues coming from these two subtractions that give us IR data. And in our case, we'll be looking at just, we'll be expanding our amplitude in the easiest crossing symmetric fashion, which is just t plus g2 t squared 0. We've set the coordinate coupling for scalars to just be 0, since we can't extract that anyway. And for fermions, the amplitude actually looks the exact same, but there is no coupling that has no s and t in front of it. So if we do this, then let me rewrite this equation on the side.
Sorry.
Yes?
Why did you use capital M to be 2m in this particular case? It was a natural length scale, and then use the subtractions to be some points between 0 and 4?
Well, we want to specifically look at massive scale, an EFT of massive scalars.
Massive?
Massive. So m is the mass of the lowest scalar. And then we assume that there's a gap above these massive scalars, which we just call the UV cutoff being capital M. So in other parts, this has just been taken to be 0. So we're usually used to having just massless scattering in our case.
So when you are massless, you have no option but to study the threshold. But now that you have a gap, why not take advantage of that and define the subtractions in between the cuts and keep the cuts at a physical location? Why would we put a new string? I'm a bit confused by that.
Well, this is just, then we wouldn't have any, then we'd basically just be integrating out our lowest massive scalar. We're just assuming that there's no particles coming after with a mass larger than m until capital M.
Maybe the question can be phrased as, why don't you have some low energy loops starting at 4 and 4?
Okay, so what we are starting off with is just tree level, but we did actually look at one loop corrections to this, which I can discuss when I get to the bounds. The main reason, this is just to basically guide us through the AdS story where we haven't looked at loops specifically. There we just looked at the flat space limit. And there, of course, we can take fine bounds for n equals 0, which corresponds to just delta phi for the scalar to be 1. But we also looked at all ranges of delta phi. So that's the first, that's the single trace operator that we'll be using. Does that answer the question?
You are measuring these G1s, etc., as an expansion around 0, right? These G1, G2.
Well, we're assuming that this that for as long that in our IR region, as long as we have a perturbative expansion, so G1, G2, we're assuming it a perturbative and small. Otherwise, we would have to include loop.
Right. But it's an expansion around s equals 0, right?
Yes. Well,
why not do it at 2m squared, like the middle between 0 and 4m squared? Then
so you mean take subtraction of s minus 2m squared effectively. You could also do that, and the bounds will be the exact same. The bounds will be the exact same. This is just nice because this is obviously symmetric in S and T, and you can take the just n goes to 0 limit of the whole thing, and it'll give you the exact same. You don't have to make any redefinitions. But you know, this will do the exact same. You might just have some linear combination, and then you have to disentangle it completely again. So specifically, we chose these subtractions in order to, I mean, this is a flat space, this is a valid expansion of n, and therefore these subtractions specifically for each k will pick out g1 and g2 one at a time. So let me actually write that down. So if we write our integral here into two parts, then the high energy part becomes an integral infinity over the imaginary part of m. And that is equal to a higher part, which is just the residue at s goes to 0 and 4m squared divided by okay. And this part is just for each k equal to gk, the way we've defined it. So that's effectively why we defined these two subtractions. So we can pick out our coefficient gk, and this is now related to some positive polynomial or positive quantity for uv, which will then give us bounds. So let me write these down. So this, I'm just going to quickly rewrite as some positive measure, which is just going to include this part and this part, times 1 over s times s squared. And from this, it's very obvious that if we now normalize by one coefficient, and we're just going to choose g1 to normalize, we'll end up using Cauchy-Schwarz to find upper and lower bounds. So this basically, for the first one, this would be basically saying that 1 over s minus 4m squared, which is just saying that the brackets are just for this measure, has to be, this squared has to be smaller or equal to 1 over s times s minus 4m squared, and this is smaller or equal to 1 over just s times s minus 4m squared. So this would be the first one, and I'll just tell you that basically g2 over g1 squared is smaller than equal to g3 over g1, which is smaller than equal to g2 over g1. Okay, so in general, the bounds will look like this. So the upper bound, and of course all of these are positive. So the upper bound looks like this, it's GL over any GK. So this is the upper bound. And this is very obvious basically from just the dimensional analysis. There's nothing like particularly crazy. And the bottom of the lower bound, here I've just decided to normalize by G1. That's a bit unknown. Oops. And this is for okay. So these are the upper and lower bounds. And basically, to say what the punchline is at the end, is we'll recover these bounds when we find bounds in AdS and take the class space limit. So in order to do this, I'm just going to quickly point out a couple things, in that these lower bounds don't actually depend on our cutoff or our small mass, apart from just some scaling. But they won't have that, and we'll see this come up again. And these have some certain just relationship at large n and small n. Right. Up to now, any questions? This is very much just the same thing as using Simon Vincent's argument and just going through the whole process in 2 dimensions. So then, let's look at this. So basically what the rest of the talk is, we'll repeat everything I just did in the first 10 minutes, and basically just do the whole thing slightly slower in AdS2 using functionals. So first, look at what...
Sorry, can I ask a question? What would be a class of theories that have in 2 dimensions that have this small m and then this separation scale? What's a good prototype of the type of theories you have?
So I mean, for small m, I wouldn't particularly know a specific theory. I mean, if you take m to be 0, you'll recover the same results as you'd have for the flux tubes. That would be a scalar, massless scalar use, basically. But I mean, for massless scalars, we basically just saw that the bounds are exactly the same at tree level from any mass. Up to
maybe let me ask differently.
Yeah.
Are there interesting theories close to saturating your bounds?
Not that we know of, not specifically. We know, so what we'll see is that the bounds themselves are saturated by some theories, but not any theories that I would say are particularly interesting. There's no case in that sense.
In the flux tube, Andrea, for example, was pointing out that it's dangerous to ignore the cuts, that you will get these gamma 3 results wrong, etc.
Yeah.
Are you not worried about the same thing?
Okay, so then let me quickly digress. So one thing we did as well, and this, I haven't mentioned this really right now just because we don't have an analog in AdS2, is that if you do add the cuts here and expand your amplitude to have the same, you work from the same Lagrangian and then you include the one loop results, we tried to use basically the same method and figure out how the bounds changed, assuming that, of course, still everything is perturbative. So if we look, I'll tell you just what the result is. So we look over G1, G3, and G2, and G9. So at tree level, they just look, the bound looks like this. So this one is just the square, so it's just parabola, and this is a straight line, intersecting at 1. And then at one loop, they shift a tiny bit, going to roughly here. This specifically also depends on the exact value now of G1, whereas for tree level, it was just the ratio that was important. So this is for some value of G1. And I think yesterday we discussed that we had, for example, this gamma 3, which is for, I believe for G1 equals 1/2, you find it, and this one lies somewhere here, some smaller than, or larger or equal to -1/768. 768. So this theory was here, and there's one that saturates this. There's S matrix that we would write down that would saturate this, and this was found, also by you and Andrea and stuff and other people. But yeah, so you have to, in order to include these theories, you'd have to include the one loop results. But specifically, this bound was found using the upper bound on the imaginary part of the amplitude. And we're really only looking at the part that, or the lower bound of the amplitude, just using the fact that it's positive. We're not using the fact that it's also bounded from above. Yeah, so in order to recover theories like this, you do have to include the one loop results, which in principle should be possible in AdS2 with using our functionals. We just we didn't go through the exact details to map one to the other. So let's look at scattering. Okay, so first note, when I say CFT1, I know that some people might want me to say CT1 or something like that. Basically what I just mean is that it's a CFT in that there's no stress tensor, and there's also no spin as we had on the flat space side, but everything else that we know about CFTs or specifically conformal bootstrap, will run the same. So all the states are in unitary representations of the Lorentz conformal group, so SO2, 1. And then you can use the irreducible components to find the primary operators that all have scaling dimension. Then these operators have some OPE, and then the correlator satisfies, the usual constraints of conformal invariance, of unitarity and crossing. And we'll be using all of these the same as we used a bunch of constraints on our amplitude. So what theory are we specifically looking at? Well, on the flat space side, we were looking at basically a weakly coupled scalar, or a weakly interacting scalar, and that basically means on the AdS side is that we want the same with some small mass, and in CFT, which is basically just some perturbation of mean field theory. So in mean field theory, we'll have one single trace operator, which will have some dimension delta phi. And this is related to the mass on the AdS side in the usual fashion. Like this. And when I say single trace operator, I'm not specifically assuming that there's a large N expansion, but I'm just using the same terminology. And then, of course, you'll have a bunch of double trace operators that come in the OPE of these two single trace operators that first have dimension 2 delta phi plus 2n. So if we just wanted to look at the massive scattering, we'd take delta phi to be 1. Otherwise, we've basically done the whole story for any delta phi. Okay, so then in one last part of CFT1, the same way that we had only one Mandelstam variable instead of 2, we also only have one cross ratio that I'll define as follows. So there's this cross ratio, which we'll then complexify. And then our 4-point function will have the following form. So if we look at scattering, phi being our single trace operator, I'll use a 4-point function as following form. I'll write the 1s and 2s to mean these x's. This is 3, 2, 4, and then z. Okay, so crossing then tells us that if we swap 2 and 4, this one stayed the same. And therefore, under crossing where x2 is swapped with x4, z goes to 1 minus z, and therefore crossing tells us that our correlator here, g of z, has to be equal to g of 1 minus z. And so the last thing we're basically missing now, before we can set up our problem with EFTs, is just the analytic structure of G. And basically G will look like this. This is the complex Z plane. It has a cut that goes from minus infinity to 0, and by crossing symmetry as of 1, we have another cut. And everywhere else, as we had with the amplitude, is analytic. Okay, so G can have some OPE expansion, and this OPE will only run over double trace operators, since those are the only ones that come in the OPE between the two single traces with our conformal blocks. And
There's
this,
not mean field theory.
yes, exactly. And basically what we now want to do is we now want to define the analog of our EFT and our UV part. So we had some cutoff on the flat space side that was M, and above that we made no assumption of a theory other than basically unitarity and crossing symmetry, etc. And we'll do the same. So we'll rewrite this as some part that is above where our dimensions are above delta gap. And delta gap will be related in the same fashion to our capital M that we had before. Just sub in delta gap and capital M instead. And here we'll just assume again that we'll have some OPE expansion, but we'll not assume much more. But below delta gap, we'll assume that we only still have double traces, and that these double traces might have slightly altered OPE coefficients and slightly small anomalous dimensions. And so instead of the writing down that I have just some sum over double trace operators, what I now want to do is reorganize this sum. So technically I have some sum over these double trace operators. But I want to reorganize this with AdS2 in mind. In that case, what I want to look at is the basically Witten diagrams on the AdS side. And each Witten diagram can be written as an OPE of over double trace operators. And but there's some ambiguity in how we write this, and I'm just going to discuss how we decide this.
So, question.
Yeah.
So now you took a step right, and you stopped discussing MFT, and now you're postulating some theory with this behavior, and
Okay.
you want to study
So
it.
basically what I'm happening is I have MFT, and I add I'm assuming that at low energy or low deltas, we still have MFT with maybe slight shifts in the OPEs, in the OPE coefficients and the dimensions. But at large delta gap, we take delta gap to be quite large, we're assuming that there might be some change.
Yeah. But you don't know if such a theory exists. You want to,
No.
given it exists, you want to study its properties.
Yes, so assuming that we can add some large operator or some operator extra or take one away on the above delta gap, we'll see what bounds we find on the Wilson coefficients that come from expanding these Wilson coefficients in the double trace operators of the low dimension operators. Okay, so in AdS2 we can only have Wilson contact diagrams that have 4 k derivatives, k being 1 or larger again, and we can write these as some sum over double trace operators. And what we want to do is we want to make contact that the flat space limit of these looks the same as one of these terms that have gk times st to some k power in them. Yeah. So in order to do this, basically we can say to the basically we can just take that the anomalous dimensions that come from these Wilson that come from these contact diagrams are 0 for all dimensions for all double twist operators and double trace operators for n equals 0 all the way to k/2 minus 2. This is for this bosons. And then on top of that, we'll choose the remaining degree of freedom so that if we take the null space of this, that if we take the flat space limit, we'll recover this amplitude. And the point of this being that if each of these comes with some coupling gk, the flat space, this gk, when we take the flat space limit over bounds, we'll recover this gk. Exactly. Okay. So then, this means that we can write this sum over double trace operators as a sum, rewritten as a sum over these contact diagrams with 4k derivatives and k to 0 with some coefficients. And so this looks very similar to what we had in flat space. We have some UV part, and we have some expansion of our IR part. And our goal now is to extract these coefficients and then use that to relate it to this UV part. And the way we're going to do this is to use functionals.
Sorry, can you say again what do you mean by this cross with the?
Oh, so this would be a contact diagram in AdS.
4K derivatives.
Yeah, exactly. This has 4k derivatives.
So here you're referring to a particular interaction in AdS.
Yes. So these are the only ones that you can have. So you can technically have also a k=0 diagram. So this will be the same as we had in flat space, where you could have had a quartic coupling, but we won't be able to extract the quartic coupling. So I mean, it could figure in, but it won't figure in the bounds.
Okay, thanks.
For the exact same reason, in that it just has running. So
are you saying these kind of 1D versions of the HTTPS solutions are just supported on a finite number of operators?
can you repeat?
Is each such term supported on a finite number of operators?
Yes.
Okay, so it's kind of
Yes.
a 1D version of the HTTPS.
Yes.
But there they're only supported on infinite number of operators. But here is
Yeah, I mean because it's 1D, it's significantly simplified in that sense.
Sorry, isn't the statement that it's not supported on a finite number of operators, right? They have you choose them such that your Nama's dimensions are
did I
0
say-
first. You said the opposite.
Oh, I
But
said
that's
the
what
opposite.
you
Yeah,
have.
no, what I wanted to say it's not supported on the first few.
so it's 0.
Exactly. The anomalous dimension for example, the first double trace operator is 0. And it has no contributions to the first k/2 minus 2 operators.
Okay.
That make sense? But it will have contributions to everything else.
Everything okay.
And specifically, we did, in our paper on the appendix, we do have these exact anomalous dimensions, both for the fermionic and the bosonic case. So then, let's look at functions. So one part I have to add as well is now what we're going to be looking at is what we're going to call the Reggie limit. And in our case, the Reggie limit just means that we take z goes to I infinity, and we call it Reggie limit mainly just because it maps the same to the actual Reggie limit in higher dimensions. And in this limit, a diagram that goes as 4 to the k has following behavior, in that it goes as z to the 2k minus 1 in this limit. So this is why we chose this exact expansion so that it didn't have any contributions from the lower operators, because we want to impose this Reggie behavior. And we'll be using this to extract it. So, that functional now. So what we want to do is we want to find a linear functional that acts on our G of Z, and that under crossing, this functional is antisymmetric. So it's following action. And because of crossing symmetry, which I wrote down here, this means just that the functional acting on g of z is equal to 0. And then this is basically the analog of what we had of our contour deformation of m over s times s minus 4m squared to some power of k being equal to 0. So this will be acting 0 on 0, and then we can plug in our expansion that we had here in UV and IR parts, and we'll have one part that's acting on this part and one acting on the UV part. So what does the action of a functional look like? Well, I'm not going to derive the complete functional. This was done by Miguel, and we'll just be using these functionals that they used. And basically what we're doing is finding a new basis of them. And a functional acting in 1D has following contour informations, in that it acts again on the double discontinuity. So omega acting on G is an integral from minus infinity to 0 of some kernel f of z, and acting on the double discontinuity of G. And in this case, what this looks like is basically you have some contour that goes in both the same direction above and below the cut. So what do we want? What properties does f have? Well, for one, in order for this condition to be satisfied, we need f of z to be equal to f of 1 minus z. And then on top of that, one part which I won't write out completely is that we need something called a gluing condition. And in practice what happens is that our f of z will be analytic basically everywhere on this plane, except for in the small region between the cuts. And in order for us to get rid of any contours that are above and below the cut, we need to relate f of z above and below the cut. And this is what our gluing condition will do. So it also has to satisfy a gluing condition. The exact condition, though, won't be exactly particularly illuminating. Okay, so what do we want to do with this omega? So we want to act on this expression on the OPE, and we want to be able to extract one of these coefficients. So some functional that we label with, let's say, k prime, acting on following term, we want this to pull out g of k prime. So I'm going to write this on the other side. So we want some omega of k prime acting on basically some contact diagram with 4k derivatives to be equal to only pull out one of these contact terms. And therefore, exactly. So how do we do this? Well, we know that these contact diagrams have a specific scaling in the Regge limit. And what we want to now do is we'll deform this contour into a contour that goes at infinity and then goes in the opposite direction of the other cut. Because of crossing symmetry, okay, well, first, as I said from the gluing condition, there would be a part that goes right here, and the gluing condition means that we can take this part to 0. This part is, because of crossing, the exact negative of this part. So what do we find? We find omega acting on something with 4k derivatives is equal to, well, first, the negative of itself, plus, well, now we have an arc at infinity, so plus the residue that we have at I at infinity. So it's 2 by I, residue as z goes to infinity of this kernel times this contact diagram. this goes as z to the 2k minus 1. So we find out that this kernel, let's say by k prime, in order for us to pick it out, we need that then f of z needs to go as z to the minus 2k in the regular limit. So using this, using the fact that we normalize it so that we have a coefficient 1, and these two conditions, we can uniquely determine these kernels. And basically, they're just some hypergeometric functions, which we can then use to extract these Wilson coefficients.
In terms of alphas and betas of NPL, are they?
Yeah. So actually, so they don't have any contributions to the alphas because they only will look at the contributions from anomalous dimensions, but they're basically a finite sum of these betas. Yeah, so for those who haven't read this, so basically the original set of functionals includes two infinite sets of functionals called alphas and betas. And the betas have basically a single zero on one of the double trace operators and a bunch of double zeros everywhere else, whereas the alphas are non-zero on one of them and double zeros everywhere else. And these functionals are just a linear combination of these betas. So basically, you have, so I think basically if you look at the first functional, it'll just combine two betas because it just has to go as z to the minus 2. So that would be basically some number times beta 0 plus some number times beta 1, because each of these betas has a behavior of going to 0, z to the, is constant at infinity, so it doesn't die off. So you need to subtract that constant term effectively from each other. You need a linear combination that goes with z to the minus 2. And then for the next functional, you take beta 2 and then subtract off the z to the minus 2 behavior to get z to the minus 4 behavior, etc. And they only have even powers just because of crossing again, because of this relation.
And can I understand this from the first line? Like betas are dual to derivatives of blocks, and this is sort of dual to the Smithan diagram.
So the way you'd go through this would be then using the definition of these contact terms in terms of the anomalous dimensions. So these only pick out certain anomalous dimensions, and then because of the contact terms having only contribution from another set of anomalous dimensions, they overlap only on if there's a certain number, exactly at one point. Any other questions? Great. So then we basically have all ingredients now to find our bounds.
Sorry, just to clarify. These f of z's are literally just z to the minus 2k.
No, so they have this behavior in the Reggie limit, and I can't exactly tell you what the exact expression was anymore because I have not written it down, but it's basically some polynomial or some fraction of n z times a hypergeometric function.
Right, sorry. Thanks.
And the hypergeometric function will show you that they specifically do have a cut at this point, but they'll also satisfy the gluing conditions, etc.
And the delta phi, was it arbitrary?
So delta phi itself, so in order to decide where you want to put your, where these zeros exactly are of the delta phi, they come in for f of z. So for any delta phi, you have a different set of these fk's.
Right. And in the other street, if I remember correctly, the kernel sort of significantly differs. It simplifies it, delta phi those two classes.
So what do you mean?
The kernel function f.
Yes.
From what I remember, it was like hypergeometric for delta phi being 3 halves or something, and then it was more complicated for.
Yeah, so what we found basically is that our kernel, it is sort of a convoluted expression at some point once you have delta. For delta phi equals 1 for boson or 3/2, it gets very simple. And the moment you choose it for any delta phi, it's a bit longer to write, basically. But what we'll find out is that these bounds, again, won't really, I mean, we'll find that the corrections to the leading order corrections will have a delta phi dependence, because the f of k's will specifically have delta phi dependence, but the leading correction, or the leading bound, sorry, won't have any delta phi dependence, because we've not really needed it other than the fact that it's sort of been part of our theory. Okay, so if we now take this functional and act it on this equation, so then acting with omega k on here, well, we'll just be able to pull this in here. So we'll have that omega prime on G, well, that's just going to be still this one. And this is for delta, again, original delta gap. But then this is just equal to GK prime. So we've been able to drop everything else. And now this looks very, very similar to what we had before. In that we had our IR observable here, that we can then take to the other side, related to some UV quantity. And what we can do, taking delta gap to be very large, then the action on these conformal blocks has following form. So there's some numerical factor here. And it has following scaling. So in particular, the actual numerical, I mean, we know the numerical factor, I'm just not going to write it down because it's not illuminating, but it is positive. So the action of these functionals is positive. Since this is positive, I know this will be positive. And interestingly enough, it actually, this sum orders itself in terms of the Casimir, which we had an input, actually. We just found this to be. Which is very nice because we'll see that this will make the flat space limit very, very easy. And so now we can basically, using Cauchy-Schwarz, do the exact same to find bounds on these GKs. So what do we find exactly? I'm going to erase this so we have more space. Well,
So you're saying even if these functionals are complicated, this hash is easy to evaluate?
exactly, yeah. So we actually, not only the hash we can also find in any order that we really want to. Just gets a bit more complicated the farther we go. But yeah, you can find it to any order you really want to. And that will also let us now write the leading corrections to our bounds. So our upper bound will look very similar. So that's just chunk GL over GK. And that is bounded by the action of the functional just on delta gap. And this is basically order, so 1 over n. So again, this factor is just dimensional analysis, and the one from how we've normalized everything. But we can find the leading correction in R squared, and this is not the same f, I'm sorry, write f or something like that. But this is basically a function of the Casimir of delta phi and L and k, which were the two coefficients that we're bounding, divided by n squared r squared plus 4 corrections. So what you can see here is when we take r squared to go to infinity, you'll actually have the Casimir theory over m squared, which will basically just give you the correction and little m squared over big M squared. And if you actually go through doing this, you'll find that this is the exact same expression as if you had taken the flat space limit and expanded it in little m squared over big M squared. But on top of that, even if you don't expand, if we have a finite large radius, we find the leading order corrections to this. And then the lower bound, we can play the same game. And then the corrections look like this. So we have 1 minus some different function now over squared. So in particular, what I want to point out in this bound is that what I'd said earlier is that this lower bound does not depend on little m squared explicitly. And you'll see this in the first correction as well, in that there is some correction for finite radius, but if you take the radius to go to infinity, all corrections die off, and you just have this exact bound, and there's no correction to it for small n. Yeah, so this also does not have any delta phi dependence, as you can see, but then this does. So this is basically what we've done. So basically, what the paper was that we were able to come up with a set of functionals that we've labeled by the Reggie behavior, and using these functionals, we can pick out specific Wilson coefficients, which we can then relate to the UV part by requiring that the Bootstrap equation is held, or is satisfied. And then when we can find bounds on this, which we found here, and in the large radius limit, we recover the same bounds that you'd find in flat space using the methods from the external EFT paper. Yeah, that was about it. Any questions?
From the 1D CFT point of view, can you put delta less than 1?
You mean less than 1?
Yeah, between 0 and 1.
No, because isn't the unitary bound?
Would it be 0 and 1?
Maybe it's zero.
Yeah, sure. No, you probably could. I don't remember if there's anything that would go wrong with the functional specifically. I can't remember if plugging in something that is less than 1 will make them not valid, but a priori, no.
You should probably worry about boundary conditions, because if delta is 0 and 1, it's probably related to Neumann boundary conditions, and then I don't know if the flat space limit is so well defined.
That's true. So one thing I sort of forgot to mention is that in order to find our normalization, we use the higher dimension of Mellon amplitude. There is actually a 1D Mellon amplitude that was done by Bianchi and collaborators, which we didn't use mainly because we couldn't really extract the large radius limit and therefore the flat space limit from it. So we use the large radius limit, so you might have to be a bit more careful for specific delta phi. But in our case, all the subtleties with one-dimensional, using it in one dimensions weren't really necessary.
So these functions are like a proper subset they're not a complete.
Yeah, so they're not in. When you take the large radius limit, you can show that this is the best you can do this. So there's no, you can actually get more information by using more functionals, because all other functionals will die off too quickly at infinity. But if you keep to the small z region, you have these alpha functionals which do have some contribution. So in theory, yes, yeah.
Could you maybe make some more general comments, like what would be the end goal of this program, or what you have in mind, what questions you want to answer?
Well, I think in this particular example, our goal was just to see was to figure out how to construct a very to make this basis shift in the functionals from this alpha and beta basis to a basis that is more that looks at these Wilson coefficients. I don't think we have any specific goals for AdS2 or questions we want to ask in AdS2. It was more of a proof of concept, I think, paper.
Do you want to do it in high dimensions? Or?
So in higher dimensions, you have a bit of more subtlety because you have a stress tensor and stuff like that. So you have to. This was explained by David in his talks, and basically they had to choose a different basis, or again an extra new basis, in order to localize over incorrect parameter. Whereas this is just using the forward limit. So in higher dimensions, there's just an extra subtlety coming from gravity, which we of course don't have here. There's no gravity.
Did I understand correctly that you have a one-to-one map between your Wilson coefficient and functionals as you go? Or no?
As in, you mean
Yeah.
this function? Well, each functional will pick out one specific Wilson coefficient. There's obviously some ambiguity in
So that's
defining
why
these
it's enough to
Wilson
pick.
coefficients, but in this, when we've gotten through that ambiguity and set them, they will map one to one. Yes. Of course, you have to also make sure that K prime is less than delta gap. So there's only a certain range that's useful on your functionals. But this also sort of relates to the fact that at some point for arbitrary high derivative orders, this stops making particular sense in business management.
Are there more questions? If not, let's end the workshop.